Hello and welcome back to Calculus 1. We are starting chapter 4 on application of derivatives. So, the first order of business is to learn about extrema of the function. So, minimum and maximum, right, singular, and minima and maxima for plural. Ooh, I almost lost the word. So we learned that, we've seen this before, that when we have a graph of some function, and the graph does whatever the graph does, we have situation when the horizontal tangent line goes through a point, and that point is always either a min or a max of a function. Now we are going to distinguish between two different types. There is going to be a local or relative min and max, and then a global or absolute min and max. The words are in different books, different words are used. So if I just write max and a min, it's not good enough. We want better. All right, we want better. And we can do better by understanding the absolute and relative or local. So if you look at the function that looks like this, you will quickly see that it has two max points. The higher one is called the absolute max, and the lower one is called the local, all relative. So they're both maximum. And then the words should make sense, right? Now, if you look at the first picture and realize that the function will go up forever, that the max that I have there has to be local, relative, right? Because all of the points on this part of the graph are higher. So it cannot be absolute maximum means the absolutely highest point on the graph anywhere. But on the first graph, we have higher points than the maximum that we are showing, which is the reason why it's local. And you have the same thing for minimum, because this one will go down forever. So when we are dealing with this min and max, to have an absolute max, it has to be absolutely largest point, or minimum, absolutely lowest point that we have for the entire graph on the entire domain. And then over here we also have a local min. So for the same reasons as I mentioned before, right, you have points that are lower than the y value for that min, so it's all local min from there. You can have a sine function that will do the wave forever. Each one of these points is going to be a global max or absolute max because they're all the same. And there are no higher points than those. So all of these will be global max. You can label them like this. Put all in the one ABS max. Maxima. Multiples, right? Multiple ones. And you have the same thing below. So this function is sine x. Maybe I should use a different color. So how do we get to figure out where is the min and the max of a function? Well, the common sense says that we have a horizontal tangent line. Because we have a horizontal tangent line, that means that the slope of the line is 0, which means derivative is 0. So, to find location of min max, set first derivative equal to 0. Now that's mechanics. There is much more to this. So this is just our preliminary thinking of what needs to happen. What we are going to do is we are going to first define something that is called critical point. And then we will find these min and max at the critical point location. So definition. An interior point of C so an interior point C of the domain of F at which f prime of C is equal to 0, or f prime of C fails to exist, is called a critical point of F. So now if you study these things, right, definitions and theorems, you know how to do problems. Because this definition clearly tells us that by setting derivative equal to 0 or figuring out where derivative does not exist, we are getting the list of all possible candidates for critical points, then therefore min and max. Now I say candidates, and I use that word because once you find the critical point, it's not necessarily a critical point. It could be something else called inflection point. And we'll see that when we cover the next section. So we start first here in this section. We start first with figuring out minima and maxima without worrying about any other stuff. And then we'll upgrade later. So what this theorem says is critical points occur at x equals to c. I should catch up. So critical points occur at x equals to c, where number 1, f prime of c equals 0, or number 2, f prime of c does not exist. So that's what the theorem actually says, the definition. Hello and welcome back to Calculus 1. This is section 4.1 where we're catching up with minimum and maximum, so part 2. Alright, let's see. So the first problem was y equals x squared. We take the derivative and we set that equal to 0. Why are we setting it equal to 0? Yes?
Because that's when the derivative is 0, which means that it changes there, which means it would be a minimum or maximum.
Yeah, because it's a horizontal tangent line, right? Whose slope is 0. Good. So we were able to find the critical point by simply setting derivative equal to 0, and then we find the critical number, and once we have the critical number, we get the, we know where the, we can calculate the y value for critical point, and then we can get the critical point. So now we know how the graph of x squared looks like. And we see that at 0, 0, we actually have a min. And it's the absolute min, actually. So I'm just going to call it absolute min. I guess we're having issues with the network here because stream should be dead again. No, it actually shows that the stream is fine. The projector is now lagging. So there has to be something, right? Come on. There we go. So I added this graph of x squared where we can clearly see that we have absolute minimum. All right, looks like that the stream is going to be difficult today. All right, so let's take a look at another situation, and that is f of x equals absolute value of x. You know the graph for this one?
Yeah.
What is it? It's a V. So what does it have?
An absolute minimum.
Absolute minimum, good.
It's not different.
Very good. So this is one of those cases where it doesn't exist. So if I try to find the derivative, I'm going to draw the function. If I try to find the derivative here, f prime of x, I actually have to use the piecewise function. Because the derivative is 1 for all values larger than 0, and the derivative is negative 1 for all values smaller than 0. And we see, now if I am to graph the derivative, it's going to look like this. Oh, I can't have equal on both sides. Oh, actually, now the way I drew it. There we go. So the black line is f of x, and the red line is f prime of x. Now observe that there is no derivative, right? So f of x is not differentiable at x equals 0, because your derivative is supposed to be a function which generates all the slopes. Now what I have over here is we have that discontinuous jump, where at the same point at 0 the derivative is trying to be at the same time negative 1 and 1, and that's not good. So because the derivative does not exist, we can conclude that we have a minimum or a maximum. Now we see it's a minimum there. So f of x is not differentiable at x equals 0, which implies x equals 0, critical number, and then f of 0 is going to be absolute value of 0, which is still 0. So we have a 0, 0 critical point. And we also know it's absolute what? Absolute min. We also have that piece of information because we know the graph. Now, this will be just one of the calculations that you guys will be running in 4.3 to graph far more complicated functions by hand. Right? So that way, in the case of apocalypse, right, you can recreate mathematics. You what? Now you have to be careful. So we know now that if you set the first derivative equal to 0, you get the critical point. If the derivative doesn't exist at a certain point, you get the critical point. But you have to be careful for those what we call false positives, right? So think about y equals x cubed. What's the derivative? 3x squared. Good. And we set that equal to 0. What do we get for x? 0. And how much is f of 0? Is 0. So we get 0, 0, right? And we got that from the first derivative calculation. So we are expecting, because we got that, to have min or a max at 0, 0. But we all know how graph for a cube looks like. Looks like this. Do we have 0, 0 min or a max? No, right? So you have to be careful of those. In this case, what you have found is something that's called inflection point, and we are going to study that in depth right after the exam, right? Because today we have 4.1 and a review, tomorrow we have 4.2 and a review, Wednesday we have exam, and then the next section. So yeah, we'll keep moving. So this is actually called inflection point. And we are going to use this much later, in 2 days, much later. So let's see, find some critical points from the homework. What does it say? Locating critical points. Let's start with problem 26. So you're supposed to take the derivative. You know what you're supposed to do, right? So f of x is equal to x to the 4th over 4 minus, what's cheap, x cubed over 3 minus 2. Here is everyone. Are you happy now? No coffee.
Is this thing messing up? Because I was trying to watch it.
Yep.
Hey, Professor.
Yes.
This one, do you recommend getting the common denominator first and then taking the?
Nah.
No, you could just take it.
Yep.
Turn that into a constant. So you could do 1/4 multiplied by x to the 4th.
True. True. So that's just the constant of it, and then make the x. Oh, I see what you're saying. The 4 times 1/4. Okay.
Oh,
You are. Geez. sorry,
What do you got?
No, we have a critical point at 0, 0. I see this with this.
It's like the praying mantis where people pick them up and, you know, they just, the praying mantis fight the people and it's like,
See you next year.
like you can really feel like that. The praying mantis. They can't stay doing something now, so they don't like. But yeah, dead people.
So the first derivative here is going to be x cubed minus x squared. That's it. And now we set that equal to 0. Remember what I told you earlier in chapter 3, that anytime you take the derivative, make sure that your answer is in factored form? This is why. Now we have to solve this equation, right? And looking at this equation, you know that the answers are clearly 0 and 1. Factor out x. X is 0. X is 1. Now, our job is not done because these are critical numbers. We need critical points. What do I do? Yeah, that's good. So plug back in original function to get y values, and there they are. So 1/4 minus 1/3 is negative 1/12, so negative 2, 24, 25 over 12. Note that I don't know if these are min, the max, or maybe that strange, or whatever we're going to call it, inflection point. So what are these? I know they're critical points, but they are something, right? So for now, since, right, you don't have the graphing calculator on the exam, so you can't graph this and, you know, look at it. The way to deal with this is very simple. Pick a point close to the x, maybe a half or negative half. It's close to 0. Because look what's happening, guys. When you have a point in space somewhere, you can get function going through it like this. In each case, it's a minimum. If you have the point in space, it could go like this, which is a maximum. Or it can pass through the point, in which case is inflection. point. So now, the common sense is that if you move a little bit to left and to right, you see over here, you move a little bit to the left, the y value is higher. The new y value is higher, which means that was a minimum. You move to the right, you see the same behavior. The y value rises, and because the both of those rise, that means that your original point was a minimum. For the max, I don't have to tell you the same story, you get it. And now for the saddle point, observe what happens there. One point is higher than your original y and one is lower. So now, if I want to examine 0, -2, I will just figure out how much is f computed at a half and f computed at a -half. I have to do both because observe that the inflection point has both. So it's not enough to calculate one side and then walk away. Because if you notice, the side that leads to a maximum here and the side that leads to the inflection point on the other one are the same shape. So if I only compute the left side and say, oh, okay, I got the lower number, so the number I got is a max, well, it could have been just continuing out of that max like this, and it's not max anymore. Now it's inflection. So you have to check both sides, whether you're lazy or not. So how much is f of a half? What was the function? Yeah, it's a fourth. So it will be 1/2 to the fourth divided by 4 plus 1/2 cubed divided by 3 minus 2. So all you're looking for with this calculation is whether the number is below or above. So what do we get? We get 2, 4, 8, 16. 16 times 4 is very good. Right? Oh wait, why multiplying by 4? It's supposed to be dividing by 4.
Because,
Oh no, it's a fraction.
yeah.
So,
The 16, so that's 1/64.
yeah. Plus 1/8 times 3, 1/24, minus 2. It's not impacted. So that's the value. Now let's check the other one out. I also have 1/2 to the fourth over 4. And now minus escapes the cube root because cube root is the odd function. So it becomes negative 1/2 over 3 cubed. And then minus 2. So 2 to the fourth is 1/2 to the fourth is 1/16, and then 16 times 4, 1/64. And then I have minus 8 times 3, 24. And then I have minus 2. So if you are comparing these two calculations, you see they went the same way, and we got the same numbers, except the sign over here is different. So now what does that tell me? Well, it doesn't tell me anything until I actually compute these values and compare them with number 2. -2. So what are we going to do?
So the top one is technically greater than the bottom.
Did you calculate the numbers or no?
Yeah, so the top one is it's negative 1.94.
And the bottom one?
Negative 2.0.
All right, thank you. So guys, here's the x-axis, and we need 0, negative 2. So 0, negative 2. When I move half a unit each side, I'm going to get, for the negative, I'm going to get the value here, and for the positive, I'm going to get the value there. So we see that this point is inflection actually, because it doesn't change, increase, decrease. We'll talk more about that next class, tomorrow. But over there we calculated the nearby points, so now I don't know how the graph looks like, but I know it goes like this through those 3 points, and I know that that's not a minimum because there's a lower point than that right here. It's not the inflection point. Technically, it is. Trying to find just awesome problems that you can enjoy, like 1 over x plus ln x. So that's problem 33. Function f of x is equal to 1 over x plus ln x. You know what to do. Derivative set equal to 0, solve the equation, get the x's, compute the y's, and then done with it. And you can test the points to see if they're min max or what's happening there. I'm gonna go get more water.
Did you send cancel the ln? Yeah. Like when I like put e to ln on both sides or whatever to cancel it?
That's working pretty well.
What's up?
The derivative of ln x is just 1 over x.
Yeah.
Yeah.
So make that? Okay.
Yeah. Just
so it'll be 1 over x.
I got negative 1 divided by x squared plus 1 over x.
Okay. Yeah. I get it.
Let's see. See you next week. We find the derivative. Well, before we find the derivative, I want to find the domain. Domain must be 0 to infinity. I can't include 0 because there's a vertical asymptote both from 1 over x and ln x at the same time. So the derivative is 1 over x squared plus 1 over x, and we need to say equal to 0. So now we just need to solve this, which is quick, right? We see that the answers are 0 and 1. I don't know if you can see that right away, but you set these guys equal to each other, right? Because you move this term to the other side, it becomes positive, so you get 1 over x is equal to 1 over x squared. When you cross multiply, you get x squared equal x. When you move everything to the same side and factor out x, you get x equals 0 and x equals 1. You get to cross out x equals 0 because not in the domain. And we end up with one critical number. So now what I do with that critical number is I plug that back in the original equation. So f of 1 is 1 over 1 plus ln of 1. How much is ln of 1? Very good. So we have our critical point at 1, 1. And the value 0 was disqualified because even though we got it from calculation, the domain does not allow for 0 because of the vertical asymptote there. Now this critical point can be min, max, inflection, could be anything. And you can test. So calculate just to see what it is, right? So calculate at 1/2 and calculate function at 3/2. Remember, the problem is now centered at 1. So we go half a unit left and half a unit right because the problem is centered at 1. So this will be 1 over 1/2 plus ln of 1/2, right? So that's 2 minus ln 2. What I did is I made this 2 to the minus 1, then minus 1 jumps in front, changes the sign, so it's 2 minus ln 2. Now that's a positive value. And we have a 3/2, so 1 over 3/2 plus ln of, well, I guess we can use the calculator to figure everything out. So what are the values? 2 minus ln 2 is approximately what?
0.57 for the whole thing.
0.57.
Yeah, for the whole thing.
And how about the one on the bottom, which turns into 2/3?
Oh no, I have 0.57 for the bottom. Sorry.
Oh, with ln 3/2?
Yeah. Sorry about that.
All right, so what's the first one?
I got 1.31.
1.31. So what do we conclude from here?
There's no change, so it's just a
It's a flexion again, right? Because 1, which is the other y, fits in between. So there we go. I want to put one more because you love it so much. Here's problem 35. So f of x is equal to x squared root x plus 1. All right, let's see what you get. What are we doing here? Nope. What's the main rule? Product rule.
What was the chain rule inside of them?
Yes.
actually makes me feel better because I'm pretty sure that this confirmed my answer was right. This one was
said 2 weeks of review for chapter 3. I have a bunch of comments. So, finish what you have in the whole thing. X squared through what's the, because you already did that. Yeah. Alright, I'll skip the stuff I do. Yeah, I just realized my mistake. Okay. So, I'll go, wait, I need to check it.
How's the product work?
Huh?
Or how's the solving equation afterwards? Oh, we see the product rule. Oh, great. Now I can't do algebra. Whoa, what are we going to do now?
Like this is the stuff that you said to use logarithmic, right?
You could.
Does it make it easier?
It could. But then, let's see. The product rule here. First of all, domain. Oh, come on. What would be the domain for this function? For the polynomial, it's all real values. And for this square root is from -1 to infinity. Right? So square root is more restrictive. So we have to follow that. So now the derivative is going to be copy first times derivative of the second plus copy the second times derivative of the first. I said plus. So now we set this equal to 0, right? The beautiful thing is that you can multiply both sides of this equation by 2 root x plus 1. Because when you multiply that, it will cancel the denominator, you just get x squared, plus 2 times 2 is 4, x, and then x plus 1 in parentheses. 0 times 2 times square root is 0. So this distributes everywhere. What do you mean positive? Oh, this is times. So now we have x squared plus 4x squared plus 4x equals 0. 5x squared plus 4x equals 0. And then the way to solve this is to kick x and have 5x plus 4 equal to 0. Set each one to 0. We get x equals 0. And x equals -4/5. Both of these numbers are in the domain, so both of these should be good in terms of extrema, minimum, maximum, or inflection point. So, what's f of 0? Anyone? Very good. And what's f of -4/5? What happened? Is everyone okay? I don't know why. Was that funny? She walked out. What happened -4/5? When you square it, you get what? 16/25? Oh my, come on guys, move a little bit. It's Monday. It's the entire week ahead of you of enjoying this stuff. Aren't you excited?
That's why we're not.
The hell?
So much is taking
Really, 4/5 squared is too much to take in? And then we have x plus 1 which is square root of 1/5. So critical point at 0, 0, and critical point in negative 4/5, comma, 16/25 square root of 1/5. Wonderful. That's critical points. Now we already discussed if you want to check if they're min or a max. We're going to have much better tools later. Remember how in mathematics you first learned the longer way, and then you say, but there's a shortcut, right? So you will have a shortcut from, working on the negative half and the positive half calculations to see if it's a min or a max. We're going to have how we do that. Great. The next concept in the same section is the supposed to be a theorem. So this is one of the major theorems, and it says a function that is continuous on a closed interval has an absolute, right? So a function that is continuous on a closed interval AB has an absolute maximum and the absolute minimum. So if your function is on the closed interval, you have a chunk of a function, you definitely have a min, definitely have a max. Now, procedure. To find ABS min or max, is as following. Find and test all critical points. So that was the first part, and then also compute function at endpoints. So that will be f of a and f of b. Yeah. So you have to be mindful of the situation where the derivative does not exist, yet you have a min or a max, like absolute value. Over here, what it says is that in addition to everything you did so far, you have to go an extra step or two, which way you want to call it. And in that particular step, you are supposed to find the y values for the a and b, and then the highest of all numbers is absolute max, and the lowest of all numbers is absolute min. So let me first make sure that you understand the concept over here. So if I have a line segment, so it starts somewhere and ends somewhere, and it does something. This one over here is ABS min. And this one over here is ABS max. Look, that one is longer than here or there. And since the graph ends here, it's not an arrow, it goes forever, graph ends, whatever the y value of this point is. Because you have 1, 2, 3, 4, 5, 6 points to consider, right? You will see that when you plug their x values into the formula, you will find this as the lowest value, because it has to. Now you have to understand, guys, that the y-axis, right, is housing the space for all the answers that you compute for the equations and so on. So looking here, I don't care how the shape looks like. For me, it was, if these two are closed dots, that means it's a closed interval. That means, right, we can, we're definitely going to have a min and a max. No questions asked. Let's see exercises, because you love that stuff. So it's the same procedure, just make sure that you also compute the endpoints. So let's see, which number? 37 through 48.
43.
Ooh. Carefully, so hold on, Comrade, look at this. This is amazing. And it goes from 0.1 to 1. How do we do this derivative?
I got a weird number, so I think I'm gonna.
Yeah, but how do we do the derivative?
Use the ln.
Use the L on both sides. Good. And then we differentiate. Yeah. It's all good. Then you differentiate both sides. You have the product rule. Alright, let's go. Let's go. Let's go down.
In my builder town hall for 5. The upgrade to 5, so you get the multi-mortar, and then you get the second double shot cannon. So it really helps your defense. I know, but it's a nice little break, you know what I mean? Like, I tell them to chill. It's a fun game. The user, I got a problem. I wish they had like all the names on there. I don't understand.
That's just for the rest of the time. It's not for the
Oh, you want to talk about eventual?
I'm gonna go use the red phone screen to execute it to the call.
And I need coffee really bad for your project. Question number 2. Could we get out the video? I was planning on the visa to do that. Yeah, well,
Yeah, I don't know.
well, I don't think there's a. I think I use it thinking about supplying the dollar. So, you know, calculation by yourself, that's fine.
Pictures.
Yeah. Yeah.
No, the castle takes dedicated bar.
You don't do that, right?
Yeah.
It's Saturday.
Perfect.
Nah, it's about 20, 25. Yeah, it's important. You want more? Do you want more?
What's the percentage?
Less than 900.
I'll finish the project this week. I'm not looking at it till Monday. Once I get an A on this test, then I can relax.
All right, so far you guys all should be caught up with this. So it's 1 over y f prime of x, right, equals to x times 1 over x plus ln 2x. So f prime of x is equal to 2x to the x times, and over here you have 1 plus ln 2x equal to 0. Right? Right. Now what? Well, you start with this, right? You always start with this. So 2x to the x equals 0, and 1 plus ln 2x equals 0. What do we do for x to the x? So how do we solve this equation? Divide both sides by 2, right? And we have x to the x equals 0. Now what? Look at the graph. Does x to the x ever touches the x-axis? No. And over here we have ln 2x equals to -1. E both sides, we get 2x equal 1 over e, right? Divide by 2. X equals what? Very good. There we go. So now we get to calculate f at 1.1 over 2e, and we get to calculate the endpoints. Oh, I didn't give you the, oh yeah, I did give you 0.1 and 1. So plug all of these one at a time in the original equation and tell me which one of these is absolute max, which one is absolute min. So what do we have for these numbers?
For the top one, I got 3.89.
Anything else? 2. We only calculated one critical point, and we have 2 from endpoints. So ABS max, that's the highest value, and ABS min, that's the lowest value. And these 2 could be min, max, or inflection, could be anything. We don't have any information, but by the theorem we are guaranteed to get either both min or max.
Is this the extreme one? Theorem?
Mm-hmm. All right, one more. Problem 59. It says find the critical points, determine the extreme values of the interval, right? So the problem is secant x on the interval negative pi over 4 to positive pi over 4. Actually, I don't know why I means.
Solve. I get secant x tan x.
Go to 0, go.
Secant x equals. Oh wait. No, that's just yeah. I had no idea. I got it. Secant x tan x. And how do I?
So you're done with calculus. Let's do algebra.
Alright, come on. So, oh wait, so maybe make the secant now 1 over cosine, and then the tangent.
If that helps. I don't know why, but that helps. No need.
Because I'm just thinking, because when sine is 0, that would invalidate it, right? Because that would send it to infinity.
Yep.
But you also want it equal to 0.
You definitely do that.
Yeah. But generally when sine is 0, it goes like,
Exactly.
exactly. So it has to be like, would it have to be sine of 0? How did you factor those apart, or are they just two separate?
Zero product rule, that's how you solve when you have factors, right? You
Yeah.
set each factor to 0. It doesn't matter. You know when you factor, you get x minus 2, x plus 2. And you set each parenthesis to 0. It's the same rule. It doesn't matter what they are. We can have anything. Negative 17, nice.
Yeah, and it's nice in here.
Negative 7. The way it should be.
the target, so each equals to 0. You get no solution because like that makes it explode. Okay, it makes sense.
Is it min or a max?
You need to calculate the other.
And you need to calculate also pi over 4. Let's go.
Because there would be endpoints. It's pi over 4. What's the other number?
So we have negative pi over 4 and positive pi over 4. So both values, negative pi over 4 and positive pi over 4, give us square root of 2. And then that will give us the, give us the square root of 2. And then after that we have the original one, which is 0. And the y value for that one was 1. So we have the absolute min here, and both of these is absolute max, right? I'm gonna do some magic now. Don't worry about it.
Oh my god.
What?
What?
I
Oh
turned
my.
a little piece of paper into this. You saw? I told you.
What did you
It's
get?
gonna be mad. I don't know.
Your wife's up.
Hey, if you don't like it, I'll
Hey,
take
pass
it.
it over. Pass it over. I'll fight you for it.
Alright.
I get the caramel macchiatos.
All right.
Wait that. Hold on. I didn't do anything.
Exactly. All right. What else? All right. So let's talk about the exam. This is it. I hope you're not disappointed. Min and max. Find the derivative set equal to 0, and yeah, done deal.